remember being in, oh, it was probably about the fifth grade or something, and I remember my teacher saying, "Of always means times," and it really bugged me at the time. But we were working on percentage problems, right? So if you have 37% of 45, right? Well, the way you calculate that is 0.37 times 45. That of means times, and they said of always means times, and it's like, what? It doesn't, of doesn't always mean time. I wasn't quick enough at the time to say, what's the name of your dog? There was an of in that sentence. Name of dog. Actually, of has two meanings. Of means times, or of is like function value, right? Name, and the notation that we use in mathematics is something like this, right? You have an input to a function and the name of the function here. So actually the name of this function is name. Name of dog. You put the dog in, you get the name out, right? And so I say be careful with notation because there's very common mistakes that are made because of the notation that we use and because of the word of meaning two different things, right? Um, Notice if you have something that looks like this, f of x, we think of x as the input to a function. F is the name of the function. Name of the function. F of x equals the output of the function. Right? So you take a number, you plug it in, you plug it into this function whose name is f, and it spits out a new number, f of x. F by itself is just the name. It's just a name. It's not anything in particular. Um, it it's just a name. Now, on the other hand, if I had something like this, this notation, 2 is a number and x is a number, so number, number, and the answer is a number, right? It's the product of those two numbers. Product of these numbers. It looks the same here. This is not f times x. This is f of x. This is not 2 of x. Well, it kind of is 2 of x because of has two meanings. Of could mean times, so 2 times x, or of could mean function of, right? Put the x into this function and give me the output. And this could be completely different than multiplying. It could be like squaring or signing or who knows what, right? It's f of x. This is 2 times x. So it's tricky when we start looking at functions like, well, the example that I did in a previous video, I had something like y equals tangent cubed of 4x squared. Um, Sorry, there was a little hair on the thing there, and I swipe it off. But um, what I see people do is they think, oh, product, tan cubed times 4x squared. They just look at this and they see times. By saying times, then they say product rule. This is not a product, right? It's not tangent cubed times 4x cubed, sorry, 4x squared. It's tangent cubed of 4x squared. In fact, tangent cubed by itself is misunderstood because it's like, do cube first or do tangent first, right? Which one goes first? And we discussed that. This is actually literally, you got to take the tangent of 4x squared and then cube that result. So this is the cube of the tangent of 4 times the square of x, right? This is not a product. I see people do this as a product rule all the time. Another thing, notationally, that I see is people think, they think like this. They say, if you take the derivative of, actually, let's do the derivative of the secant, right? The derivative of the secant is the secant times the tangent. And we might say that, but we get in trouble because of that, right? Secant is just the name of a function. It's not a value. It's not a function. Secant of x. Now we're talking, right? Now we got an input, we got the name, we get an output, and we can take the derivative of that output function. And the derivative of the secant x is the secant of x times the tangent of x, okay? Places where I see that being an issue is when someone has something like this. They got the derivative of the secant of x squared, for instance, and they say, oh, derivative of the outside function is secant tangent, and I'll leave the inside alone, but then take the derivative of the inside. And so they get this thing that looks like this, and it's like, wait, what's this secant doing all by itself? The thing is, the derivative of the secant is not secant tangent. The derivative of the secant x is secant x tangent x. So the derivative of secant squared x, so not that, is the secant of x squared. Sorry, secant of x squared is the secant of x squared tangent of x squared, then times the derivative of the inside. Okay. And now doing this, I see here's another notational thing that looks kind of funny sometimes, is because what's the difference between sine of x and sine x? Are they the same or are they different? I mean, I have parentheses here, I don't have parentheses there, right? They're the same. With trig functions, we quite often leave out the parentheses. I should have secant of x squared, tangent of x squared. And that becomes an issue too, because when, like without those parentheses in there, I see people look at this and say tangent x squared times 2x, and they say, oh, well, that's tangent of 2x cubed, right? That they combine these two together. It's like, whoa, 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 wait a minute. The x squared is inside the tangent, the 2x is outside the tangent. They will never combine, okay? So anyway, there's some notational things that you got to keep track of, right? Be aware that there are these issues and pay attention to your own work. Anyway, there you go.